We're now going to engage with some calculation related to group sequential clinical trials. For this sample calculation, we're going to simplify things a little bit, but this is very similar to the methodology that's used in general when identifying significance thresholds in these group sequential designs. The setup for this problem is what we have on screen right now. I'm going to give a short overview of it. So we imagine we're running a single-arm clinical trial, and we're trying to evaluate the efficacy of a new treatment. And we have a continuous outcome Y that's measured on each patient who we enroll in this trial, and it indicates if they have a positive or negative change in health status after they take this treatment. So positive Y would indicate a positive change in health status, negative Y would indicate a negative change in health status. And one might be interested in understanding the expectation of Y, the expected change in health status after a patient has taken this new treatment. The null hypothesis is perhaps that the expectation of Y is 0, that the health status will on average be unchanged after a patient has taken this new treatment. Just to note that in practice, you have to be very careful running a single-arm trial with no control arm and evaluating a null hypothesis like this. Something like placebo effect or time trends might result in an expectation of Y that is non-zero when in fact treatment is not actually effective. However, we're still going to engage with this simple scenario, as again, this will generalize to more complicated problems as well. So let's imagine we plan to enroll n total patients, but would like to perform an interim analysis after half of the patients have been enrolled. So after n over 2 of the patients have been enrolled, we would like to run a hypothesis test evaluating if this null hypothesis can be rejected. If we do reject the null hypothesis, then we can stop the trial and either claim that we have a great success or that treatment is harmful if the treatment effect lies in the wrong direction. If we fail to reject the null hypothesis at that interim analysis halfway through the trial, then we continue enrolling until we have a total of n patients in the trial and then run an additional hypothesis test at the end using all n patients. It's common that we would like to control the overall level of the trial at, say, 0.05. That is, if in truth the expectation of Y is 0, we would like to reject the null hypothesis a total of only 5% of the time, and that has to include either rejecting the null hypothesis at the interim analysis or at the final analysis. So to do this, we would like to identify a threshold alpha that we can use at each of the two analyses that we can compare our p-values to, such that our overall probability of committing a type 1 error is maintained at 0.05. So just to give an overview, so we have the trial start. We have analysis 1, so analysis 1, and then we have analysis 2 that we potentially get to at the end. And again, we would like the probability of rejecting at either of these two analyses, or the probability of rejecting at least one of them, to be controlled at 0.05 if the null hypothesis is true. And to ensure this, we're going to have to use a significance threshold when looking at the p-values at each of these two analyses that is more stringent than 0.05. For example, if we try to use alpha equals 0.05, then the probability of committing a type 1 error at only the first analysis would be 5%, and we would accumulate additional probability of committing a type 1 error by running the second analysis. So as we will see, with alpha equals 0.05, that threshold for each analysis, we would end up with an overall type 1 error of maybe close to 8%. So again, we're going to need a threshold that is less than 0.05, and we're going to see how we might calculate that. There are going to be two pieces. The first is we need to engage with the joint distribution of the two test statistics, the statistic calculated here and the statistic calculated here. They're going to be correlated because the statistic calculated here includes all of the patients used in calculating the statistic here. Once we understand the joint asymptotic distribution of these two statistics, then we're going to see we can run a Monte Carlo simulation to identify the value of alpha that we should use. So to begin, we're going to let Zn denote our test statistic at the end of the trial, and this is going to be a t-statistic. So it's going to be the sample mean of the outcomes divided by its standard error. In this case, that's going to look like sigma over square root n. And for the moment, I'm going to assume sigma, the variance of the individual y's, is known. However, one could replace sigma by sigma hat, making these actual t statistics rather than z statistics without changing their first order asymptotic behavior. And again, y bar n just denotes the sample mean of all n observations. And the test statistic at the interim analysis, I'm going to call Zn over 2 to indicate that we only have half of the observations. I'm imagining n is an even number here. And this is equal to y bar n over 2 over sigma over square root n over 2. So both of these are t statistics. At the final analysis, it includes all of the observations. At the interim, it only includes half of the observations. Now we know that under the null hypothesis, that the expectation of y is 0. So under h naught, Zn, as n gets large, should converge in distribution to a normal with mean 0 and variance 1. And similarly, Zn over 2, as n gets large, should converge in distribution to a normal with mean 0 and variance 1. And these are both by the central limit theorem. So now we're interested in the distribution of Zn and Zn over 2 as a vector. And we actually have, under that null hypothesis, that this converges jointly in distribution to a normal still with mean 0, and now with the covariance matrix sigma, where here we know that the diagonal entries of sigma are each 1, and we're not sure yet what the off-diagonal entries are, what the covariance between these two statistics is. Now, just to note, it's a little subtle to show this convergence in distribution. Actually, it doesn't quite follow just from the vanilla multivariate central limit theorem, but you could apply the multivariate central limit theorem with a little bit of care and get that this holds. I'm not going to go into those details, but I think that's an interesting exercise. So to identify what goes in these question mark boxes, what we're going to need to do is actually calculate the covariance between these two statistics. So the covariance of Zn with Zn over 2. And we're just going to write out actually what these things are. So this is the covariance of y bar n over sigma over square root n with y bar n over 2 over sigma over root n over 2. Now, the first rule we're going to use is that constants can be factored out of a covariance. So this is going to be square root n times square root n over 2 over sigma squared times the covariance of y bar n with y bar n over 2. Now we're just going to focus on this term for a second and try to simplify that down. So we're going to do that by actually just expanding out each of these. So this is the covariance of 1 over n times the sum over all n observations of yi with 1 over n over 2 with the sum of just the first n over 2 observations of yj. So again, we can factor out these two. So we get that this is equal to 1 over n times 1 over n over 2, covariance of, again, the sum I equals 1 to n, yi, sum j equals 1 n over 2, yj. And now the covariance actually distributes over sum, so it turns out we can move both of these sums to the outside. So this is equal to 1 over n, 1 over n over 2, sum over the i's, sum over the j's of the covariance of yi and yj. Now, if I is not equal to j, then these are our outcomes from two totally different people, so we're going to imagine they're independent. If I is equal to j, then these are identical, so this just becomes the variance of yi. I is equal to j for exactly n over 2 of these terms, and for all the rest, I is not equal to j. So this is just going to be, again, we have these first two terms out front, times, they're going to be n over 2 terms where I is equal to j, and the variance of each yi is just sigma squared. Right, so we can cancel these out, and this is just going to give us sigma squared over n. So now, if we'll recall from before, we had covariance Zn with Zn over 2 was equal to square root n over 2 over sigma squared covariance y bar n over 2. And if we take this and just plug it in for this piece and do some cancellation, what do we get? We get that this is actually just the square root of 1/2. So what does that tell us? That tells us then that Zn over 2 converges in distribution to a normal with mean 0 and covariance matrix that looks like 1, square root 1/2, square root 1/2, 1. So this is now the asymptotic joint distribution of our test statistics. And we are interested in understanding what the probability that one of these or the other will exceed our cutoff, which is determined by alpha, right? And we want to identify an alpha such that that will only happen with 5% probability. So I want to find alpha. So find alpha such that the probability that Zn is greater than or equal to phi inverse 1 minus alpha over 2, or Zn over 2 is greater than or equal to phi inverse 1 minus alpha over 2 is equal to 0.05. Just to note, those are very poorly drawn capital Phis that are meant to indicate the CDF of a standard Gaussian. This expression is exactly the probability that our p-value at the interim analysis or p-value at the final analysis for a two-sided hypothesis test is less than or equal to alpha. So we would like that probability, the probability of having a type 1 error, to be equal to 0.05 or maybe less than or equal to 0.05. Our goal is to identify the proper value of alpha to make that happen. There's not an easy analytic way to do this, so we're going to do this using a Monte Carlo simulation. All right, we're now going to write some code to identify that value of alpha that we need to use such that the level of our trial is controlled at 0.05. The first thing we're going to do is add in a library for generating multivariate normal random variables. So this MVT norm library you might need to install, and this just makes it very easy to generate multivariate normal random variables. As we move forward, we're going to write this code in a little bit of a pedantic way, but in a way that I think will help structure things for our understanding. So we're going to create 3 functions. The first function is going to generate data from a trial. Or maybe I should say generate a pair of test statistics from a trial. The second function is going to evaluate if either of those test statistics is less than alpha, so evaluate if we can reject the null hypothesis in that trial. And the final function is going to do both of these many, many times to generate a large number of trials and evaluate the overall level of the trial design. So let's start with that first function. Here we want to generate data from a single trial. I'll call this function genTrial. It's not going to have any arguments. So we're going to generate a bivariate Gaussian vector, again with mean 0 and variance covariance matrix that has 1 on the diagonals and square root of 1/2 on the off diagonals. So RMV norm is a function for generating a multivariate Gaussian random variable from that library MVT norm. We only want to generate a single pair. We want our mean to be 0, 0. And we want our covariance matrix sigma to be this matrix with 1s on the diagonal and square root of 1/2 on the off diagonal. And that's all that this is going to do. We are then going to return this value in test stats. Our next function is going to take in both the outcome of gen.trial, that pair of statistics, and an alpha level, and going to evaluate if the results from the trial are significant. Now remember, the results are significant if either of the p-values corresponding to those test stats are less than alpha. Make a function eval trial. It's going to take in two values. One I'll call stats, and the other I'll call alpha. And I'm going to do this in a couple of steps. The first thing I'm going to do is calculate the tail probabilities from this bivariate vector stats when I compare it to a normal random variable with mean 0 and variance 1. So tail.probs 1 minus. So again, this is going to calculate that sort of two-sided p-value corresponding to both the interim analysis and the final analysis. So it's going to give us two p-values for two-sided hypothesis tests, right? If the value in stats is large and positive, then it's going to look at the right side tail probability. If the value in stats is large in magnitude but negative, then it's going to calculate a left-hand tail probability. And now, because we're running a two-sided test, we want to compare each of these tail probabilities to alpha over 2 and see if any of them is less than alpha over 2. So let's make a new variable. And we're going to use the any function, which returns 1 if any of the arguments in the vector passed in is true. So again, we're comparing these two tail probabilities to alpha over 2. So we get a vector of trues and falses in here, and then we evaluate if any of them is true, and if so, then we get a true or a 1. If not, then we get a false or a 0. And then we are just going to return that output. So again, this is a function that takes in these pair of statistics, the z-scores or t-scores that we get from the first interim analysis and from that final analysis, and then evaluates if either of them is significant when comparing to a two-sided test with significance threshold alpha. Now finally, we want to use both of these functions and run a Monte Carlo simulation that generates data from many trials, evaluates for each of those trials if there's a significant finding, and calculates the overall level. So we create a function that I'll call check level. And it's going to take in an argument alpha and an optional argument nsims, the number of simulations to run, and I will set the default to 100,000. The first thing to do is to use a replicate command to run all of those trials and then evaluate which of those are significant. So I'll make a variable for that called runs. I'm going to replicate this nsims times, and each time I'm going to run eval.trial on gen.trial alpha. So let's just remind ourselves what this does. So nsims times, it runs gen.trial to generate a pair of statistics, and then it takes that pair and plugs it into eval.trial with significance threshold alpha. So what are we going to get at the end of this? We're going to get nsims, or by default 100,000 different trials where the output will be a vector of 100,000 trues or falses or ones and zeros, indicating if there is a rejection or not in each of those trials. And then I would like to return the proportion of those that are 1, so that can be the mean of that vector. The mean of a binary vector, or the mean of a vector of trues and falses that gets converted to a binary vector, is the proportion of 1s. So now we're going to run each of these lines just to get them in our R session so that we can engage with those functions. And now we might check what the level is if our significance threshold is 0.05. So again, the significance threshold at each test here is going to be 0.05, and we want to check the level overall in the trial. This is going to take a couple of seconds, so I'm going to fast forward through that. And we see from this Monte Carlo simulation that it looks like if our significance threshold is 0.05, if that's the alpha that we use, then the level is actually roughly 0.08. So we have some inflation of that type 1 error. So now, rather than just trying alpha equals 0.05, we might want to try a number of different candidate alpha values so that we can identify which alpha value gives us an overall level closest to our goal of 0.05. So to start, we'll create a vector of alpha values. So maybe we'll set the lower bound on this of 0.025 and perhaps the upper bound on this of 0.04. And here we're going to include 10 alpha values. If you had more patience than me, you could try more, and you could change the lower and upper bounds. I think these are potentially appropriate for getting us to our target level 0.05. Now we want to run the check level function with each of these alpha values. To do this, we're going to create a new vector called levels. And we're going to use the sapply command. The sapply command takes in two arguments. One is a vector, and then the other is a function to apply to each element of that vector. So our vector will be alphas, and our function will be check.level. Now, if we run these two lines, we will create our vector of alphas. We can look at those. And now we can evaluate the level for each of those different alphas. This is going to take a little while, so I'm going to skip ahead. All right, now that that's done, we can evaluate the levels of the trials run with these different alpha values. We'll begin by evaluating this visually with a plot. So we're going to plot the alpha values on the x-axis, the corresponding levels on the y-axis, with lines connecting the points. And now we can add a horizontal line at a level of 0.05, and that helps us evaluate roughly what alpha we would like to attain that level. And here we see that the alpha we might use is slightly less than 0.03. We could also engage with this more quantitatively by looking at both the alphas and the levels together. And here we see that to attain a level of 0.05, we need an alpha value between 0.028 and 0.03. So maybe 0.029 would be appropriate. So again, if we wanted to be more precise, we could do this in a more fine-grained way, or maybe now we could rerun this, except rather than using this range for the alphas that we are considering and evaluating, we would use a much smaller range, the lower bound being this, perhaps, and the upper bound being this. One final piece, I wrote this code in a computationally very inefficient way. My goal was to make it clear what each piece of this was doing, and I probably used too many functions. I probably could have written all of this in a single function, and just in general, calling that random multivariate normal function over and over is going to be much less efficient, I would imagine, than just calling it once and creating lots of replicates. Similarly, we didn't need to generate a new 100,000 trials each time we tried a new alpha value. We could have kept the same trials and just compared them all to a sequence of alpha values. So again, I think there is value in writing computationally efficient code. There is also value in writing very clear, very clean modular code. So as an exercise, you might try to write this in a much more computationally efficient way.